Hello guys and welcome to another TensorFlow tutorial. Today I'll be showing you guys how to make a custom layer with custom gradient. So without further ado, let's just start coding. So obviously we're going to import TensorFlow as TF as always, and then we're going to actually make a class. Let me just add this a few lines so that PyCharm doesn't complain about formatting issues. So we're going to be replicating the dense layer, so I'm just going to call it my dense layer, and then we're going to extend off the layer class, so layers.layer. Then now we have to make an init function. We're going to want to pass in the input size and the hidden size. Then we'll just initialize W. This is not really needed, like all these initializers, these next three lines that I'm going to do, but I'm just going to put them on so it's easier to convert this to make it more robust, which I'll explain to you guys later, how you can make it more robust. So yeah, we're just gonna write over W now, which is self.add. We're gonna self.add weight, and then we're just gonna name this W, then shape equals input size, then hidden. It's actually self.hidden size. We'll just leave it at that so long. So this is, we can just copy paste this into somewhere else to make it more robust in the future. Then we're gonna have an initializer. It's gonna be random normal. Then we have to set trainable to true. Okay, cool. So after that, what is? Oh, okay. So yeah, we forgot something really important, which is we have to add this line in. And actually I have to add in the class name as well, comma self, and that should, yeah, okay, that works. Then we want to do the same for W as well, but W is going to be a bit different because the shape is actually, it's just the hidden size, and we'll just add a comma afterwards. Okay, just need to check trainable to true randomly. I think we can, for now we'll just send this, but normally you just set B to B0, that's fine. W has to be randomly initialized so that it's not symmetrical, because if you set it to 0, then it's just all the neurons are going to basically do the same function, do the same operation to the same inputs, so the function's going to be symmetrical. Well, the operation's going to be symmetrical. So what we want to do next is want to just create the call function. This is going to be the forward pass basically. And this would just be return tf.mat_small tf.matmol, and then what do we have to do with this again? Oh yeah, so this would be solve.w, and then I'm just trying to think now if we think it would be soft, so yeah, okay, so it has to be x first, and then yeah, solve.w, and then we plus solve.b. So this is how you just replicate like a dense layer, and also this is actually the unindent this. That should be fine. Okay, so yeah, just format that. So this is without like a custom gradient. This is just, you can use TensorFlow's functions to build your own custom layer, and as long as you're using TensorFlow's functions, TensorFlow will be able to keep track of the computational graph. But if you want to create your own function with your own gradients, you'll have to actually make your own TensorFlow function with a custom gradient. So to do that, we'll just we'll have to start with tf dot. Well, we'll just call this custom. We'll make the function quick gradient. Then we're going to take in a w, a b, and an x. And then we have to decorate the function. Just return. Decorate the function with tf dot custom gradient. There's no brackets of that, so cool. Okay, so forward pass is the same as up top here. So let's just copy paste this and take out the solves. By the way, also note that the this function is actually outside of the class, but you can put it in. But like, yeah, it's better to. It's fine if you have it outside as well. After that, we actually gonna wanna do the backpropagation. So we wanna create the gradient function. So that's gonna take in DLDZ, which is the gradients that have been backpropagated through the network. So we take that in. And before actually I go into this, I'm gonna explain to you guys how I came about these formulas and like where I got them from, etc. So you guys can follow along easily and explain to you a bit about that. So I'll see you there. Okay, cool. So these are the standard formulas for computing the gradients for a fully connected layer or a dense layer in TensorFlow's case. So first I want you to notice that the input data x at the bottom right over here, it's in, well, each training example is in its own column. So like a training example would be like one image or one row of a table if you were working with tabular data. But yeah, so as you can see, TensorFlow actually stores the data in the opposite way that was in the previous slide. So like it's actually the rows are for each training example. So that's why we're gonna have to tweak it a bit. So to get these formulas that I have in front of you over here, what I've actually done is I've just transposed x, so like the TensorFlow x of t, and I'm multiplied by dldz. DLDZ is also like transposed from the previous slide. So this DLDZ is this DLDZ but transposed. Then yeah, I did that for both W and X. So I basically just transposed this W or the X and I swapped these two. The DLDB is basically the same as before because it's just straight up a DLD, well, the bias gradient is basically a DLDB is just this DLDZ. It's straight up just equal to that. The catch for that is that we actually are working in batches, so we have many DLDZs. It's not like exactly so this would be like 100 vector, but this would be like 32 by 100. So what we're gonna have to do is that we're going to have to sum across the batching dimension. So that would be the first dimension. But yeah, that's all you kind of need to know. So yeah, let's continue coding. So from the previous slides, we actually need to compute two things quick before do anything else. So we want to compute the transpose of W and then transpose of X, tf.transpose, and X, easy as that, TLDW. So DLDW was actually just tf.matmul of X of t DLDZ if you can remember, and then DLDX is equal to tf.matmul of DLDZ and W of t. And then DLDB I said was equal to, so DLDB is equal to tf dot reduce sum of DLDZ axis. So it was actually just equal to DLDZ, but we're gonna want to sum this, so let's just sum quick. So tf dot reduce sum, and then we're gonna do it across the batching dimension, which is 0, and then we want to return DLDW, DLDB, DLDX. The order of this is very important. First of all, I just want to make two comments. So the order of this is very important. It has to be the same order as the parameters are passed into the actual, like, the function. This should be custom operation. And second of all, this W has to be the same dimension as this, B has to be the same dimension as this, X has to be the same dimension as this, or sorry, this has to be the same dimension as X for this to work, or else TensorFlow is gonna throw some errors. After that, we just have to return, the Y, of course, and then we have to return grad function, but we don't actually return the function, we just return the point. Well, we don't return like a value from the function, we return the function itself, so we don't put a bracket at the end there. So after that, actually just gonna put this in here, and then we're actually gonna change this to custom operation, and then that should be the same. So I'm just double checking everything looks good. So let me just show you guys how to actually use this. So it's just if name equals main, then I'm just gonna pull in, we're gonna use MNIST to test this, so x train, comma, y train, comma, x test, comma, y test. Then we wanna pull in the tf.cures dot dataset dot, and then we want MNIST dot load data x train. So we want to actually pre-process x train first. It's 28 by 28 by 1, so we want to kind of reshape it so that we can flatten it into a two-dimensional tensor. So what we're going to do for that is we're going to go x train and then -1, so TensorFlow is going to infer the dimension, well, the value of this dimension, or how big this is, and then the image is 28 by 28, so that's why we're gonna add, we're gonna do 28 by 28. Then we're just gonna put this to float 32. I don't think this is really needed, because when we divide by 255.0, I think it will change that to float 32 anyway, and we'll do the same for x test. So let's just do that, copy paste this for x test. Cool. Alright, so let's just first, I just want to print, because we're going to do this, we're going to do a test for both the custom dense layer and the TensorFlow's dense layer. So just want to print this, gonna make like a heading there basically, and off that we're gonna actually create our model, so with our custom layer in it, so tf.cures.sequential sorry about that. And then tf.cures, we want an input layer layers dot input, and then shape is equal to 28 times 28. That's fine. Off that, put a comma at the end, and then we wanna put in our dense layer. So the input's gonna be 28 times 28. And then we want also the output size, or the hidden size. This would be 64. And then just copy paste this. 3 times. Okay, so we actually have to. So this is we're gonna feed a dimension of 64 in here. So we're gonna want to change this to 64. We can lower this. This is gonna be 32. This will be 10. After that, we'll actually. I think that's it actually. Um. Then we'll add model 0.compile, and then we want to just set our so losses equal tf to curious dot losses dot sparse categorical entropy, and then from logits equal to true. So basically, normally we'd put it into a softmax, but since we're not putting it into a softmax, we're going to say it's from the logit, so it's going to apply the softmax and then it's going to apply this loss function. Yeah, and after that we will just do optimizer equals tf.curious.optimizers.atom, and then we'll just have the default learning rate, so we don't need to actually add anything. After that we'll have metrics. This is obviously accuracy. TensorFlow's, well, Python's getting in the way. Accuracy. After that we can just fit the model o dot fit x train, y train, and then we're just gonna do for 5 epochs. And we'll evaluate it on the test set. Evaluate x test, y test. Cool. And then, so I said we're gonna do this for both our custom layer and also our, well, TensorFlow's dense layer. So let's just change this. So TensorFlow. No, I'm not at the right one. This is TensorFlow. I just want to add this up here quick, so we know when it ends. We're going to change this to an equals, a double line to show that it's done. Put this at the bottom here as well, so I don't forget it later. TensorFlow dense layer. Okay, so we want to change this to. So with PyCharm, you can just middle click and, well, not middle click, sorry, you click on your scroller and you just drag and it does this like a block highlight. So tf.curious.layers.dense, and then we don't need this and we don't need this. Sorry, we don't need the first numbers. 64, and this would. So you can see the difference between our layers right here, just in terms of like when you initialize them, you have to add both the inputs, but TensorFlow kind of just infers the size. So yeah, everything seems to be set up, so we can just actually run this. Oh, we got an error. What is this? It's not callable. Oh, I think I did something. Yeah, forgot the dot reshape. We have to reshape this. All right, let's run this again. Oh, another error. Okay. Object has no attribute x. Not x. We have to not double check this. So let's just change this quick. Solve.w, solve.b, and then we don't put in solve.x. We put in x. Cool. All right. Let's try this one more time. This should work. Cool. There's it working. So yeah, after this is done training, I'll get back to you guys. Alright, cool. So it's done. We can see that the results are very similar. So it starts off at like 80, 89%. This starts off at like maybe 89.5. This is 88.5, so a percent higher. Then afterwards it gets to about 92. This gets to 92.35, but the TensorFlow actually beats it out by a fraction of a percent in on the test set. But this is basically due to how the weights are initialized. And yeah, that would depend on like maybe this first layer got better initialization weights and was able to train faster. But yeah, they seem quite similar and there's very little difference. Okay, let me just tell you guys how you can make this more robust and you don't have to actually add in an input layer. So what we can do is instead of having an init, well this code in init, we can actually make a bold function, and this is called when TensorFlow gets the input shape, and maybe the model's compiled. I'm not completely sure when this is run. It's run like in different scenarios, but basically it passes in the input shape, and we can use this input shape to actually initialize our weights, and we won't have to actually get in the input shape from the function initialization. We actually get out when TensorFlow finds out the input shape and bolds the neural network. So let's just change our code so that it fits. And this would be -1 because we want the last input shape. We can also just put 1 here because we're expecting a 2-dimensional input. But yeah, let's just leave it at -1 so that it's more robust. After that, we actually have to change this. So let's just, so we don't need any of this, and our layers are basically equivalent now. And if we run it, it should work. But yeah, that's how you create a custom layer with custom gradient in TensorFlow. Hope you guys enjoyed. Please leave a like and subscribe if you want to see more content like this. Also drop a comment if you guys want to see anything, if you guys want me to explain or make a tutorial on something that you guys are confused about. Hope you guys have a great day. Bye.